Magazine!
Hello everyone, this is Gauzar, the self-proclaimed physics detective. Before I go any further, I feel compelled to warn you that there will be some spoilers ahead. Today I'm presenting my findings on an investigation I've conducted into the execution of Captain Jack Sparrow. At the end of the first Pirates of the Caribbean, Captain Jack is sentenced to death by hanging for his crimes of piracy. Thankfully, our protagonist is saved by Will Turner, who throws a sword into the support framework below the gallows. Thus, instead of falling to his doom, Jack is able to support his weight on the sword. The question that I seek to shed some light on today is whether or not the sword could have actually supported his weight. In order to answer this question, we have to talk about stress. Stress is, essentially, the pressure that forms in a solid object in response to some kind of load. The reason we want to talk about stress is that any given material will break, regardless of its shape and loading conditions, if the stress reaches what is called the ultimate strength. To determine if the sword will break, all that must be done is determine what the maximum stress in the sword would be and compare that value to the ultimate strength of the material that it is made of. Being stuck on one end and free to move on the other, the sword acts as a cantilever beam. Other examples of cantilever beams include traffic lights, flagpoles, and balconies. To analyze a cantilever beam, we want to look at a specific kind of stress, which is called bending stress. Maximum bending stress is calculated using where the Greek letter sigma is the maximum stress, M is what's called the internal bending moment, and S is the section modulus. In the case of Jack standing on the sword, the internal bending moment, M, is given by the product of his weight and the distance along the blade from his center of mass to the wood support. In order to obtain a value for M, we'll assume that Johnny Depp is 160 pounds, and based on the size of replica swords available online, that his weight is centered 1¼ feet along the blade. The next step is to determine the section modulus. The section modulus is a value that represents the beam's ability to withstand bending stress based on its shape. For example, imagine two rulers. If you take the ruler on the left and you try to bend it like this, you'll find that it's much easier than if you tried to bend the one on the right like this. To understand why, imagine that the rulers are made of tiny blocks glued together. When you try to bend either ruler, you are literally trying to crush the blocks on the top and pull the blocks on the bottom apart. The blocks in the middle, however, don't experience anything due to bending. In other words, the only parts affected by bending are the top and bottom. So, the ruler on the left is easier to bend because most of its blocks are in the middle and therefore aren't helping at all. In terms of stress, the ruler on the left will have much higher stress because there are fewer blocks resisting the bending, and therefore each individual block has more of a burden to carry. To determine the section modulus for the sword, we have to consider its shape. We can see that Will threw it so that the broadside of the blade was face up, like this. So next, let's assume that the blade has a roughly rectangular cross-section that measures 1 1/4 inch by 1/4 of an inch. Doing so gives a stress of 1200 megapascals, or 184,000 psi. To determine if the sword would break, we need to compare it to the ultimate strength of the metal that it is made of. So let's look at a table of some typical steels to see how they hold up. As you can see, there are some metals that could hold up his weight, and others that definitely would not. At this point, I could keep going and make a case either for or against the sword breaking, but I'll leave that up to you. As you consider everything that I've presented, consider also the following. First, the value of 184,000 psi was calculated using nothing but assumed values. If I overestimated Jack's weight or the distance between him and the wood support, then the actual stress would be much lower than what I've calculated. The same could be said about the stress if I underestimated the dimensions of the blade. On the other hand, the blade was assumed to be perfectly rectangular. The more the actual blade deviates from this assumption, the higher the stress will be. Finally, everything that I've done has been for what is called static loading. What this means is that we've completely ignored the fact that Jack landed on the blade and have treated everything as if he was just slowly eased down onto the sword. If impact is taken into account, it will increase the max stress, potentially far beyond the breaking point. Anyway, that's enough for me. If you think the sword would have held up under Jack's weight, let me know why in the comments below. If you think that it should have broken, again, tell me why in the comments below. If you like this video and you want to see more like it, then why not show your support by clicking like on this video, subscribing to my channel, and telling your friends. If you have any ideas for my next investigation, you can send an email to gauzar@yandex.com. Or you can visit my Facebook page at facebook.com/physicsdetective. Speaking of my Facebook page, it's a great place to go to check out news on upcoming videos. Well, this is Gauzar, the self-proclaimed physics detective, signing off.